Okay, so that was the velocity law of the wall, also known as the universal velocity profile. There is the equivalent thing for temperature, right? So this is a heat transfer class, so we probably should think about that. But you get it the same basic way. You go to your energy equation. So this is our Reynolds averaged energy equation. Over here on the right side, we have this apparent heat flow that is composed of both a molecular and a turbulent component. So this is our apparent heat flux. If we restrict ourselves to being in that same region of the boundary layer that's close to the wall, then these terms become not very important, and we're left with only this term over here related to the apparent heat flux. So if we get rid of these terms, then our differential equation becomes that the rate of change of the apparent heat flux must be equal to 0, right? So dq dot apparent dy is equal to 0, which says that the apparent heat flux, just like the shear stress, the apparent shear stress in that quick flow region has to be constant. And because we're right next to the surface, that apparent heat flux is equal to the heat flux at the surface, your convective heat transfer rate. So this is your differential equation then, right? The apparent heat flux is Q dot S, and it's composed of a molecular component and a turbulent component. In a laminar flow, of course, you'd only have K, and this would tell you that you'd have a linear temperature distribution. Here, because this turbulent thermal conductivity is going to be varying and getting larger and larger, you would expect that you don't have a linear temperature distribution anymore, at least not outside of the viscous sublayer. All right, so we can come up with solutions for the thermal law of the wall, as it's sometimes called, and we can do that using any kind of model that we can come up with for this eddy diffusivity of heat transfer. We have all these models, and actually more, for the eddy diffusivity of momentum. We know that the eddy diffusivity of heat transfer is related to the eddy diffusivity of momentum through this turbulent Prandtl number that's typically taken to be something like 0.91. So any of these models, if I just divide by the turbulent Prandtl number, I'll have a model for the eddy diffusivity of heat transfer, right? So we have to do some algebra to get from here to a model for theta plus. It's all pretty doable algebra. The first thing we're going to do is the same thing we did before for our momentum equation, and that is take this differential equation and try to express it in terms of inner coordinates, since, if we move back one, the models that we're going to be using are expressed in terms of inner coordinates. So I have to remember that theta plus is defined in this way, right? So if I have a derivative of t bar, that's going to be a derivative of theta plus multiplied by my normalizing, or my eddy temperature fluctuation, which is Q dot S double prime divided by rho C U star, right? So this dt bar became d theta plus multiplied by this guy right here. And then the same thing down here, I have a derivative of y, that becomes a derivative of y plus multiplied by, this is the characteristic length of the viscous sublayer. That's what this is. So all I did is make those substitutions. You can see I have a u star times u star, so a u star squared on the bottom. If I remember that u star is the eddy velocity, which is defined as the shear stress over rho square root, then u star squared must be just equal to the shear stress over rho. So I made that substitution here as well. What did I do next? I made some cancellations that are pretty obvious. So on each side I have this heat flux, I can get rid of that. On the top and the bottom I have the shear stress, I can get rid of that, and I'm left with this equation here. So I'm closer. I'm going to take this rho c and bring it into the parentheses. So K over rho c is the molecular thermal diffusivity, and then if I divide this turbulent thermal conductivity by the product of rho and c, I'm going to get the turbulent thermal diffusivity, which is the eddy diffusivity of heat transfer. So that's what I have left. Over here I have a mu over rho, which is kinematic viscosity. So if I bring that inside of here, I'll have alpha over rho, and then here I have epsilon sub h over alpha over nu. Here I have epsilon sub h over nu. And in order to express this part of the equation in terms of epsilon sub m over nu, which is what my models have, I'm going to multiply and divide by epsilon sub m. So what am I left with then at the end? Here I have 1 over the molecular Prandtl number. So this is a property, right, of the fluid. This is my epsilon sub m over nu. This is the model for turbulence that I'm going to install here in order to get a solution. And then this is the turbulent Prandtl number, which is, regardless of fluid, always going to be about 0.91. So this is the differential equation that I got to solve in order to get my thermal law of the wall. So we'll use the same model that we did before, the Prandtl-Taylor model, which is a really simple two-layer model, right? So no turbulent eddies out to y plus equals 11.5, and then linearly growing turbulent eddies beyond that. Okay, so if I take this differential equation and I substitute in 0 here for below 11.5, I get this differential equation, which I can integrate to get that in the viscous sublayer, or at least in the region of the flow that I am modeling as having no turbulent eddies, I get a linear temperature distribution, which is not surprising. In that region, I'm only dealing with molecular conductivity. So if I move out then beyond 11.5, I have to do a little bit more algebra, but it's not too bad here. So let's see. Beyond 11.5, I'm going to substitute this part of the model in here, and that gives me this differential equation here. So that's fine. I'm going to separate and integrate. So I'll take d theta plus and put it on one side. I put all of this y plus stuff on the other side. I'm going to integrate. Again, I can't integrate all the way from the wall. I have to integrate starting at y plus equals 11.5. So that's the lower limit here. At y plus equals 11.5, theta plus is the Prandtl number times 11.5. So that's the lower limit here. The upper limit is theta plus here and y plus here. So this is a big ugly thing to integrate, but it's not that hard if you remember your calculus substitutions. I'm going to call this denominator w plus. So w plus is that stuff. dw plus is what? Kappa over PR turbulent times dy plus. I'll make these two substitutions into here. So let's see, the denominator becomes w plus. The numerator becomes dy plus. So the numerator is dy plus. It becomes dw times PR turbulent divided by kappa. So this is a much more integratable thing. I've expressed the limits here I've expressed the limits here as w at y plus equals 11.5 and w at y plus equals y plus. So this becomes then PR turbulent over kappa, and then the natural log of this upper limit divided by this lower limit. So this is my temperature distribution as I get out beyond 11.5. So my solution is here then, right? This taking this this differential equation and substituting in this model, I get these two different regimes, right? They sort of match up. They actually match up right at 11.5. They have very different behavior below 11.5 and above 11.5. And we can look at this and sort of see some interesting behavior. So I guess first thing is obviously at 11.5, y plus equals 11.5, I get discontinuity, right? So what I'm plotting here is this inner temperature difference. So theta plus as a function of inner position. So y plus, if we just go back one, you can see that theta plus is a function of yes, y plus. It's a function of PR turbulent, which is like 0.91. It's a function of kappa, which is 0.41, so those are just constants. It's also a function of the molecular Prandtl number, though, so I'm going to get different behavior depending on what kind of fluid I'm talking about. So I plotted this for a few different Prandtl numbers, ranging from, this is like an ideal gas up to a more viscous fluid. So, you get this different behavior, but depending on whether you're below 11.5 or above 11.5. Below 11.5, what you're looking at here is actually a linear temperature distribution. Again, the log scale makes it look like it's nonlinear, but this is a linear temperature distribution. Above 11.5, you're getting a logarithmic temperature distribution. There's some interesting stuff to look at here. One thing to look at is that, or to notice, is that Prandtl number seems to matter kind of a lot. And where it matters is actually in the viscous sublayer, right? So why is that the case? Why would the molecular Prandtl number matter so much for a turbulent flow? Well, you have to remember that in a turbulent flow, the viscous sublayer is really the dominant characteristic of the flow, right? So what is the Prandtl number? The Prandtl number, the molecular Prandtl number is kinematic viscosity over thermal diffusivity. And if you substitute the definitions for these two things into this equation, you'll find that it's really setting the viscosity over the conductivity, right? So Prandtl number you can think of as setting this ratio of viscosity over conductivity. So if I want to think about the, where did my pointer go? If I want to think about the thermal resistance of the viscous sublayer, which is the biggest thermal resistance in a turbulent flow, it's going to be how far do I have to conduct the energy, which is the distance, the size of the viscous sublayer, which is at least proportional to this characteristic viscous sublayer length scale that we found before, right? We could say it's maybe 5 times that, but it's proportional to that. So that's how far I have to conduct the energy divided by K. And K here is the molecular conductivity of the fluid, because in that viscous sublayer, that's all I got going on is molecular diffusion. So this is your biggest resistant, right? And if I plug in this definition or this scaling argument for how big the viscous sublayer is, so that's what I've done here, you can see that this resistance is proportional to the viscosity over K. It's proportional to the Prandtl number. So a molecular Prandtl number is going to have a large molecular Prandtl number, right, is going to give you a large viscosity. It's going to give you a very thick viscous sublayer, so you have to move the energy farther, right? It's also going to give you a small thermal conductivity. So you have to move the energy farther through a less conductive material, right? It's everything you don't want in terms of having a good heat transfer fluid. So this resistance of the viscous sublayer is proportional to the Prandtl number, and you can clearly see that here, right? The temperature drop across the viscous sublayer is really large and gets larger and larger as the Prandtl number gets bigger and bigger, because the viscous sublayer is getting thicker and it's getting less conductive. Now, on this plot, it doesn't look like the viscous sublayer is getting thicker, but that's because we've normalized by this viscous sublayer length. So actually, in a physical, a plot of temperature versus Y versus temperature versus Y plus would actually show that these viscous sublayer lines are extending farther out into the flow. Once you get beyond the viscous sublayer, once you get out here into the turbulent core, you can see the resistance isn't changing at all, right? These lines, there's no more temperature rise here than there is down here, and that's because the molecular Prandtl number really doesn't matter anymore. It's all turbulent eddies out here, and it just doesn't really matter that much. If we were to plot this on a linear scale, you could see the behavior that we talked about before, which is that, you know, we're going to get pretty much all the temperature drop across the viscous sublayer. Once you get outside the viscous sublayer, you know, you sort of have a superhighway for energy to get out into the core, right? And so you get this very sharp gradient that's confined very close to the wall, and that distance over which that gradient occurs is related to how big that viscous sublayer is.